Hey physics class, so we've been doing calculations on circuits with resistance and current, and I want to try a different approach to maybe try and sidestep some of the ways that you've been getting stuck. Another tricky thing about this is that every circuit is so different, it's hard to find a one-size-fits-all solution to this. I want to try and help you understand how circuits work so that any circuit you try to solve will be possible to you. So I'm going to start with a circuit, and it is going to be like this. One battery, one resistor. Let's say the battery can be 10 volts, and then the resistor can be 10 kiloohms. There we go. Well, that's a really basic circuit. And if we're going to use Ohm's law on this, V equals IR, and we got a voltage of 10, a resistance of 10,000, which means a current of, let's divide both sides by 10,000. 10 divided by 10,000. It's 0.001. So we have a current of 0.001 amps, aka 1 milliamp. Okay, so that circuit was simple beyond belief. It was hardly even worth doing. However, let's just say that that one resistor wasn't actually the circuit. Let's just say that was equivalent. So let's split up this resistor into two resistors in series. Okay, let's just say this was the simplified version. Let's do the real one. And now I think I'll do this one in a different color so you can keep them separate. So here's the real resistor, right? The one as it was before it got simplified. Still 10 volts, however. Two resistors. Now, because these are in series, I just need two resistors that add up to 10,000. And that shouldn't be too hard, just two numbers that add up to 10,000. Let's go ahead and make it 40,000 and 60,000. I'm sorry, 4,000 and 6,000. Whew, I'm not that bad at math. So 4 kiloohms here. 6 kiloohms there. Now, you'd recognize those as being in series. They should add up to be the same. However, now that we have two resistors, we should actually be able to calculate the individual resistances across each, individual voltages across each one. So resistor 1, resistor 2. Okay, so why don't we go ahead and find out what that voltage is. So I can think of two ways to find the voltage. One way I can think to do it is to say R1 is 40% of the total resistance, so R1 will have 40% of the voltage drop. And according to this, 40% of 10 volts should be 4 volts. Same thing would be true of R2. Since it's 60% of the total resistance, it should be 60% of the total voltage. So just off the bat, I'm going to say I think 4 volts drops across this and 6 volts drops across that. But I want to be a bit more precise. Do we know how much current is going through these resistors? Well, yes, we just found that. There's 1 milliamp going through each one of these. How do we know it's 1 milliamp? Well, we know it's 1 milliamp because that's the current going through this. These two are in series, which means the same current goes through them. Okay? Same current goes through resistors in series. So since 1 milliamp goes through this, 1 milliamp must go through those. So I can set up Ohm's law. V equals IR, knowing that the current is 0.001 amps and the resistance is only 4,000. Well, I just need to multiply those together. So 0.001 times 4,000. It's 4, just like I thought. The resistance across, the voltage across this resistor is 4 volts. And there's only 6 left for that one. But I'm out of space anyway, so I'm not going to do that calculation. But that one should be obvious to you, that if I have 4 volts gone here and 10 total, there's only 6 left for this. Okay, well, I'm not done unsimplifying it, so let me get a new sheet out, and we're going to take this and expand it even more. Right, so we had a 10-volt battery. We had a 4 kilo ohm resistor and a 6 kilo ohm resistor. So let's get this going. So 10-volt battery. There's my 4,000. Now I'm going to split up my 6 into 2 that are in parallel. All right, so this one should be kind of tricky. Again, 10 volts. This is still 4 kilo ohms. But now I got to figure out 2 resistors which in parallel could give me 6,000. Now, just from the point of view of trying to make a problem, I'm looking for a solution to this. 1 over 6,000 equals 1 over x plus 1 over y. I need to find 2 numbers that might possibly satisfy this equation. And in order to make this work, I just need to choose one, and then I can solve for the other. So knowing how this works, 6,000, the 2 resistors in parallel that make 6,000 are both going to have to be higher. So I'm going to just choose one of them to be 18,000. So 1 over 6,000 equals 1 over 18,000 plus 1 over, I don't know, whatever the last one is. This isn't math that you would ever have to do, mind you, to solve a circuit. I'm just trying to show you how a problem gets made. So let's see here. 1 over y is going to be 1 over 6,000 minus 1 over 18,000. Sorry, that k is for 1,000. So I just need to flip that. So it'll be y equals 1 over 6,000 minus 1 over 18,000. All right, let's see what that is. So clear this. 1 over, parentheses, 1 over 6,000 minus 1 over 18,000. Ah, 9,000. How nice. We got a nice whole number. It's almost like I knew that would happen. So 9,000 will do it, which means I could have an 18 kilo ohm resistor here and a 9 kilo ohm resistor there, and together these two in parallel would make a 6 kilo ohm resistor, and the 6 and 4 kilo ohm resistors in series would make a 10 kilo ohm resistor. And if you'll remember, that's what this problem has been all along. So let's see what everything will be. So first off, we already know that this is going to be 4 volts because we already did that work on the last page. So we can go ahead and start with knowing this will have 6 volts across it. Okay, So knowing that there's 6 volts across this thing, remember, that is equivalent to this, okay? I'm talking about, here, let me fold this so you can just see that. These are the same thing, or at least they function equivalently. So that 4,000, it's the same, and this 6,000 kilo ohm resistor is equivalent to this parallel group. So the 6 volts that was across this must also be across this. 6 volts across that, 6 volts across that. There's no way to get around it. So, I probably shouldn't have thrown that. I'm going to want that later. Oh well, foresight. So, let's solve it. Using Ohm's law, V equals IR. So, I know that the voltage is going to be 6 volts. I don't know what the current will be across either of them, but I do know what the current will be across both of them. I know that the current through this is 1 milliamp, which means there's 1 milliamp coming this way, but it won't be split up evenly. Which side is going to get more of the current? The one with more resistance or the one with less resistance? Well, the one with less resistance is going to get more current because it's easier to go that way. And in fact, if you add these up, 9 plus 18, that's 27. There's only a third of the resistance on this side, and there's 2/3 of the resistance on that side, which means this side should get twice as much current as that side. But let's see the math work out. This current should be twice of that. So let's do the current across the 9 kilo ohm one. All right, we'll do this one. So we don't know what the current is, but we know that the resistance is 9,000. So if we want to get the current, we're going to need to do 6 divided by 9,000. And so let's go ahead and calculate that. Clear? All right, 6 divided by 9,000. It is 0.000, 6 repeating. That is a lot of numbers. Okay, so the current here is going to be 0.0006 repeating amps. Holy cow, that is not a lot at all. Remember the prediction, this should be twice of that because the resistance is half here. It should be twice as easy for electricity to flow here because the resistance is half. So I'm expecting this to be 0.0003 repeating. But let's do the math. Let's not assume. V equals IR. Voltage is 6. Current is unknown. Resistance is 18 kilo ohms. 18,000. I have to do 6 divided by 18,000. I think you know where this is going, but I have to do it anyway because it's like teacher law. 6 divided by 18,000. There it is, 0.0003 repeating. Not a surprise at all. So let's see, where can I write this that it won't get lost? Maybe I can write it right here. 0.0003 repeating amps is the current right there. Okay, well, I've taken a single resistor. See, I knew I would want that sheet later. Oh, here it is. I found it. So I took a single resistor. I broke it into 2 that were in series, found that 10 volts still went across it. It was just 4 volts here and 6 volts there. Then I took this resistor and broke it into 2 that were in parallel. 6 volts across this means 6 volts across that. What about the current? 1 milliamp went through this. Did 1 milliamp go through these? Yes. If you add these 2 together, you get 0.001. 1 milliamp still went through this. It just went mostly on this side and a little bit on that side. So, whenever you have a circuit that you're trying to solve, to find the resistance. I'm sorry, I keep saying find the resistance. To find the current and voltages on individual resistors, what you want to do is think about how you might have gotten that complicated arrangement from a more simple version that might help you understand how to break it down. So, since this video has only been about 15 minutes, I'm going to go ahead and do a complicated one. I'm going to really hate myself because usually physics problems are designed to have a simple solution, and I'm just going to make one up, which means I'm going to kind of give myself difficult awfulness to do, and I am not going to like that. But you know what? I haven't embarrassed myself in anybody in like weeks because I'm not in front of anybody. So here goes. I already regret this. It's going to be a good one. Okay. Can do this. You can do this. You're breathtaking. All right, let's do this. Let's see. Let's have a 12-volt battery. And then we can go ahead with, let's see, one. Let's go ahead and have 2 here, 1 there, and how do we make this more complicated? Ooh. Oh, I'm going to hate myself for this a lot. Oh my gosh. Oh, I want to just crawl in a pit and light it on fire. Ah. Ooh. All right. So this is Can I quit yet? All right. So this circuit is going to be it's going to be a monster. But I said I would do it, and I'm a man of my word. So here goes. This will be resistor 1. Resistor 2, resistor 3, and resistor 4. This can be resistor 5, and this can be resistor 6. Let's go ahead and give some values to those. Let me see if I can make this up to make it slightly less awful. All right, so let's say, oh man. Resistor 1 can have a resistance of, oh, yikes. All right, so 2,000. All right. Resistor 2 can have a resistance of, I'm full of all the hate. All right, so 3,000. Resistor 3 can be 5,000. Resistor 4 can be 4,000. Resistor 5. Let's let that one be 4,000. And then resistor 6 is see, 2, 3, 5, 4. I guess we haven't had a 1,000 yet. Oh, okay. So, if this doesn't make you wish for a swift end of the world, then I don't know what would. Just kidding. It's a science problem you had once in high school. This is no big deal. Let's fix this. So, let's look for ways that this could have been made from something simpler. So right off the bat, I see that these two resistors could just have been stuck together. So let me get another sheet of paper, and just little bit by little bit, I'm going to replace these. You know what? No, I'm going to do this differently because I don't have a whiteboard, but you know what I do have? Post-it notes. So I'm going to just step by step replace these with post-it note twins. So I'm going to take resistors 3 and 4 and add them together. into a single equivalent resistor. All right, so resistors 3 and 4, they are 5,000 and 4,000. Add those together. Again, I don't really need a calculator to add 5,000 and 4,000, but if I don't add them, I get like sued or something. So 5,000 plus 4,000 is 9,000. I've got a 9,000 ohm resistor here. Okay, what about next up? So I can see these two in parallel, because if you're going to go along this way, that is a path that you can take. So those two are in parallel. I've got a 9,000 in parallel with a 3,000. So if I'm going to replace those, I need to do the reciprocal adding thing. So let's go ahead and do that. 1 over 3,000 plus 1 over 9,000. Whoa! 2,250, which means these two in parallel are equivalent to a single one that is 2,250. So on you go. Yeah, I'm just going to keep using black. All right, so 2,250 right here. See, 2,250. So just in case you forget, this 2,250 is made of those two in parallel. And just in case you forget, this 9,000 is made of those two in series. But you wouldn't forget because you're good students. So let me put that back down. Good. Replace that with a 9,000. Replace those two with a 2,250. All right, now what? Look at those two. They're in series. See that? Which means you can replace them with their simple addition. This one is 2,000. This one is 2,250. And so let's just add those up. 2,000 plus 2,250. 4,250, which means we can drop a marker. Yep. Which means we can take those two and replace them with this single 4,250. This is looking a lot simpler now, isn't it? So what I have now is those two in parallel and then that one in series. So resistor this and resistor 5 in parallel. You have to add them up the parallel way. So that would be 1 divided by parentheses 1 divided by 4,250. And then add to that 1 divided by, what was R5? Oh, 4,000. R5 is 4,000. 1 divided by 4,000. Hey, our first non-whole number, 2,060.6. I feel like we should get a prize or something because we finally have something that's not a whole number. So 2,060.6 is just this whole thing. 2,060.6. That looks really boring now, doesn't it? And you're like, no, actually, it looks nice and safe. I agree. 2,060.6 is the equivalent resistance of that whole side. Finally, adding that whole thing together, R6 is 1,000 ohms. So those two adding up, it's going to be 3,060. Let me just add 1,000 because it's teacher law plus 1,000. It's 3. Oh, I hit too many ones. Oh, that's embarrassing. All right, so let me just go ahead and do that again. 2060.6 plus 1000. Like, seriously, I did an unnecessary math problem on a calculator and then I messed it up because I'm a champion. 3060.6 is the total resistance. It needs a post-it note, otherwise I'm Ooh, oh, can I get it on that? I don't think I can fit it. Oh no. Or Nah. Oh well. I've unfortunately messed up my space, so can't replace the last one. Sorry. So what I did get though was a total resistance of 3060.6. Oh, I think that went into the calculator. Here you go. 3060.6. Okay, so what do I do with that? Well, now I know the total current in the entire circuit. So now I'm going to have to put some paper down here so I can do my calculations in and slowly strip things away. So I got V equals IR going on here, and I know that the voltage for the whole circuit is 12, and I know that the total resistance was 3060.6. So I times 3060.6. I got to divide 12 by this. It's like not fair. 12 divided by... Oh, sorry, that was plus. Oh, the plus sign and the divided sign, they look so similar sometimes. So, 12 divided by 3060.6. Not a lot. 0.00392. All right. So the total current in the circuit is 0.00392. So here's what that means. In resistor 6 is that much current. There's that much current in resistor 6. That also means that we can figure out the total voltage drop across resistor 6 because we know how much current is in it. So let's go ahead and do that. So I'm going to, oh, I know what I'll do. I'll write it in different colors. So let's go ahead and work this out. So if the voltage across resistor 6 is equal to the current across through resistor 6 times the resistance of resistor 6, I know what the current and the resistance are. The current is 0.00392 and the resistance is 1000. All right, let's multiply those. 0.00392 times 1000. 3.92 volts, ladies and gentlemen. So let me write this in a color. The voltage across resistor 6, 3.92. And the current through resistor 6 is 0.00392. I know that's written kind of small, kind of has to be so that it can fit, but if you look very closely, hopefully on a big screen, you should be able to see the voltage is 3.92 and the current is 0.00392. Okay, let's go ahead to this resistor. Well, I know what the current through it is. I don't know what the voltage across it is. So instead of doing V equals IR, I'm going to do this. I know what the total voltage of the circuit is. It's 12. Here's 3.92 of it. So how much is left for this? It's got to be 12 minus 3.92. 12 minus 3.92 is 8.08. So if there's 12 volts in the circuit and 3.92 of them are here, then the voltage across here should be 8.08. By the way, it's the same current as that, so let me write that in. The current is 0.00392. But wait, that resistor's not really there. It's actually those two. So, what stays the same and what's different? Well, one thing that's the same is they have the same voltage. They must have the same voltage across them because they are in parallel. What will be different is the current. So I can go ahead and write in here that the voltage is equal to 8.08. That looks terrible. That's 8.08. What about the current though? Well, this is a simple Ohm's law problem because I know the voltage and the resistance. So let's go ahead and do that. V equals IR. The voltage is 8.08. The current is unknown. The resistance, what's the resistance for resistor 5? It's 4,000. So is that all in frame? Yeah, just making sure it's all there. So I already forgot. 4,000? Was that it? Yeah, 4,000. So if we want to know the current through resistor 5, it's going to have to be 8.08 divided by 4,000. 8.8, oops, 8.08. Gotta clear that. 8.08 divided by 4,000. 0.00202. 0.00202. 0.00202. Okay. Look, if you can't read this, at least you can read it on the calculator. I'm sorry, I am trying to cram it into a small space. Okay, so we know the voltage across this one. It's the same as that. It's 8.08. Voltage here is 8.08. We can also figure out the current with Ohm's law, or again by subtraction, because I know the total current is supposed to be, oh, sorry, I moved that out of frame. I know the total current is supposed to be this much. That much went the other way, so I could just do that number minus that one. Let me go ahead and do that. I'm going to do this number minus that one. We'll see what we get, and then we'll check it. 0.00392 minus 0.00202. I get 0.0019. So I'm going to just predict that I get a current here of 0.0019. Let's see if that works by Ohm's law. Let's see if V equals IR. If I do 0.0019, that's I, times R, 42, oh, what did I do? I did something wrong. Starting over, 0.00, come on, 0.0, oh, I'm sorry, I couldn't see the space where I was typing. 0.0019, that's I, multiply that by R, times 4250, look at that, I get V. 8.075, that rounds to 8.08. It agrees. It must agree, because, you know, it's physics, and physics is right or something. So I'm going to get rid of this, because this is now obsolete. I'm stuck with this. But wait, that resistor's not even really there. This resistor is made of those two. Those two are in series, which means they have different voltages, but the same current. I know what the current is, 0.0019, so I'm going to go ahead and just write that in, that the current right here, what I think I'm going to try using a finer tipped pen. Let me see if I can make it more legible like this. 0.0019 is a current that either became easier to read or harder to read. I don't know which one it is. I mean, that seems legible on my screen, so hopefully it's still good for you. The current here must also still be 0.0019. It can't help but be the same because they are in series. However, the voltages are different now, and we can use Ohm's law to figure out the voltages. So let's go ahead and do that. I'm going to need some fresh paper. So first off, V equals IR. Let's do this for resistor 1 first. We know the current, 0.0019. We also know the resistance. The resistor of resistor 1 is 2,000. That should tell us V. 0.0019 times 2,000. That's looking a little faint to me. I'm afraid that's not legible. Oh, I wish I could get feedback. 0.0019 times 2,000 is 3.8. Oh, there's 3.8 volts across that. Very nice, resistor 1. Very nice. So 3.8 volts here. That's not a check mark, that's a V. Okay, so what about this? Well, once again, Ohm's law. Or we could remember that there used to be 8.08. Now there's 3.8, which means there's a little bit more than 4 volts here. But you know what? I'm not going to go by my intuition. I want to be really rigorous and make sure I get all the decimal places. So let me go ahead and do V equals IR. I is 0.019. R is 2250. Like I said, it should be a little bit more than 4. .0019 times 2250. See? 4.275. Now, because of the way significant digits work and how complicated this math is, I may be accumulating several rounding errors. I'm not going to worry about that. I'm just going to go with, yeah, that's a little bit more than 4. It's just like I thought. So this voltage here is 4,270. I'm sorry, 4.275. But that resistor's not even really there. This is actually those two in parallel. So do those two have the same voltage across them or the same current through them? They should have the same voltage across them. They both have 4.275 volts across them. So let me write that in. This is voltage equals 4.275. This one is voltage equals 4.275. What about their current, though? Okay, so there's two ways to solve this. One is, I know that it must be 0.0019 because that's what that is. So these two must add up to 0.0019. Also, since since R2 is 3,000 and this is 9,000, basically I have to cut this up into fourths, give 3 of the fourths to the easy way and the last fourth to the hard way. But I mean, you know, then Ohm's law would just be looking at us from across the room with all these like sad eyes, and we'd feel bad, and we'd be like, all right, Ohm's law, come over here. And it'd be like, yay, you get to use me. So let's go ahead and use Ohm's law. Ohm's law. New pen because I'm tired of blue. Ohm's law looks like this. I know what the voltage is. I know what the resistance is. I don't know what the current. Can you see that? Yeah, okay, good, we can see that. So the voltage, let's do R2 first. The voltage across resistor 2 should be the, oh, wait, I'm sorry. I know what the voltage is. The voltage across resistor 2 is 4.275. That should equal the current, which we don't know, times the resistance, which we do know, which is, R2 is 3,000. So we're going to have to divide 4.275 by 3,000. So 4.275 divided by 3,000. Yep. Okay, 0.001425. That is a tiny, tiny little current. 0.001425. Current is 0.0014. I'm going to call that 3. I'm going to round up because I don't think I could fit that whole thing in there. Okay, so how much current must be over here? Well, a third of that. I mean, I could just divide it by 3, but once again, Ohm's law feels unloved and unwanted, and I don't want to make any law of nature feel unloved and unwanted because I'm a physics teacher, and so, okay, I'll use it. V equals IR. The voltage is 4.275. The current is unknown. The resistance is 9,000. So I got to do 4.275, 4.275 divided by 9,000. That should be a third of the other one, 0.000475. Let's be consistent now. Current equals 0.000475. I'm curious, if I triple this, will I get that? Times 3. Yeah, I got it. See? Okay, last one. Last one. This is not really here. That's actually what we had. 2 resistors. I know what the current is. It's this, because that passes through them both. So I can go ahead and just pen in that current. The current equals 0.000475 on each of them. But they'll have different voltages because they are different resistances. They will be close to each other because resistors 3 and 4 are close, but they won't be the same. Resistor 3 has a higher resistance than resistor 4. Which one will have a greater voltage? The one with a higher resistance will have a higher voltage because it is going to get rid of more energy. So let's just Ohm's law this thing to bed and it will be done. So V equals IR. I don't know what the V is, but I know the I, it's 0.000475. Sounds like I'm saying a phone number, times a resistance of, was that one 5,000? Yeah, that one's 5,000. Okay, well, let's do this thing. 0.000475 times 5,000. It's 2.375. Okay. Oh my goodness, we're almost done. 2.375. Last one. We have a unknown V, but we have a known I. 0.00, I'm sorry, 3 zeros, 0.00475 times a resistance of 4,000. It's going to be 80% of this other one. 0.000475 times 4,000 is 1.9. Wow. Whew. That is it. All the resistances gave us all of the voltages and all of the currents. Alrighty. Ooh, sorry, I just had to reach for something. I'm gonna make sure things don't die while I'm using them. Okay. So let's just make sure everything adds up that ought to add up. For example, all of the voltages should add up to 12. And I don't mean like 2.375 plus 1.9 plus 4.275 plus 3.8 plus 8.08 plus 3.92. That's not what I mean. What I mean is, as you pass through this circuit, no matter which way you go, you should pass through 12 volts. So let's just pick a path. In fact, yeah, let's just pick a path. Let's go this way. Resistor 1, resistor 2, resistor 6. There's a path, right? Okay, so 3.8. Let's add them up. Am I clear? All right. So 3.8 from resistor 1, then resistor 2 plus 4.275 plus 3.92. 3.92. See? 12 with a rounding error. 11.995. All right, let's try another way. Let's go the long way. Okay. So let's just see if that works. So 3.8. So that's through resistor 1 and then 3.4. So that would be plus 2.375 plus 2.375 plus 1.9 plus all the way around 3.92. There we are at 12 again. Okay, so we've taken resistor 1 both times, but just for a second, note how the only difference between those two roots was whether we took resistor 2 or 3 and then 4. This is why resistors 3 and 4 must have the same voltage across them together as that one by itself, because that's the only way for that to be the only difference between the two roots, and they both equal 12. Anyway, just a side step. We never took R5, so let's do that one. So let's do R5. So voltage across resistor 5 was 8.08. Add to that 3.92. Yeah, it's 12. Okay. Cool. Here's a quick question. I don't want to throw you off or anything, but like, what would happen if we went the wrong way? Like, here's what I mean. What would happen if we went like this? Oops. Will we still get 12? Actually, we will. Watch this. So I'm going to see if I can trace the path with one hand and enter the numbers on the calculator with the other. So I start out. So I go across 3.8. 3.8. Okay. Plus 4.275. 4.275. Okay. Now I'm headed the wrong way, as in I'm headed back towards the positive post. So instead of doing plus 8.8, I actually need to do minus 8.08. Now, go across R1 again, plus 3.8. Now we'll go all the way plus 2.375, 3.275 plus 1.9. This is getting out of hand. All right, and then all the way over, plus 3.92. Hmm, 12.89. What did I do? Oh, look. I was supposed to put in 2.375. I put in 3.275. Oops. Well, take away the 1, that fixes it. So my bad. But the point is, you still get 12 unless you make a typo, like a smart person. Can I fix? I can't fix that. Oh well. So I don't want to have to add all that up again. So just yes, mistress, just me, if you don't mind. Okay. Well, that's all the voltages. Let's make sure the currents work out. The current here was 0.0019. The current here is less than that. But these two currents add up to it. Okay? So watch here. 0.00143. Remember, it was actually 25, but I rounded it to 3. Plus 0.000475. That gives me back my 0.0019. Okay, how about this? This current is 0.00202. 0.0019 went that way. 0.00202 went that way. Let's see what they add up to. 0.0019 plus 0.00202. It's 0.00392, which is equal to that. Okay? So the way that these work is that whenever you've got two resistors in parallel, the same... I look like I have a tiny head and huge hands. Whenever you've got two resistors in parallel, the same voltage will be across them, but different currents. Whenever you've got two resistors in series, the same current will be through them, but different voltages. All right, well, it's been about 50 minutes now. That's like a whole class period almost. And I've barely even taken a drink of water. Man. Hey, I hope this isn't too rough on you. I hope that this is helpful and not just making your head spin and wish for school to be over. Hey, it's going to be good. Anyway, that's circuits, that's voltage and current and all that stuff. Let's be done.